Hello friends, how are you? And welcome to my YouTube channel, Random Knowledge. Today's video titled, How Stars Are Formed. So without wasting any time, let's get started. Stars form inside relatively dense concentrations of interstellar gas and dust known as molecular clouds. These regions are extremely cold, temperature about 10 to 20 Kelvin, just above absolute zero. At these temperatures, gases become molecular, meaning that atoms bind together. Carbon monoxide and hydrogen are the most common molecules in interstellar gas clouds. The deep cold also causes the gas to clump to high densities. When the density reaches a certain point, stars form. Since the regions are dense, they are opaque to visible light and are known as dark nebula. Since they don't shine by optical light, we must use infrared and radio telescopes to investigate them. Star formation begins when the denser parts of the cloud core collapse under their own weight, gravity. These cores typically have masses around 104 solar masses in the form of gas and dust. The cores are denser than the outer cloud, so they collapse first. As the cores collapse, they fragment into clumps around 0.1 parsecs in size and 10 to 50 solar masses in mass. These clumps then form into protostars, and the whole process takes about 10 million years. How do we know this is happening if it takes so long and is hidden from view in dark clouds? Most of these cloud cores have infrared sources, evidence of energy from collapsing protostars, potential energy converted to kinetic energy. Also, where we do find young stars, we find them surrounded by clouds of gas, the leftover dark molecular cloud. And they occur in clusters, groups of stars that form from the same cloud core. Protostars. Once a clump has broken free from the other parts of the cloud core, it has its own unique gravity and identity, and we call it a protostar. As the protostar forms, loose gas falls into its center. The infalling gas releases kinetic energy in the form of heat, and the temperature and pressure in the center of the protostar goes up. As its temperature approaches thousands of degrees, it becomes an infrared source. Several candidate protostars have been found by the Hubble Space Telescope in the Orion Nebula. During the initial collapse, the clump is transparent to radiation, and the collapse proceeds fairly quickly. As the clump becomes more dense, it becomes opaque. Escaping infrared radiation is trapped, and the temperature and pressure in the center begin to increase. At some point, the pressure stops the infall of more gas into the core, and the object becomes stable as a protostar. The protostar, at first, only has about 1% of its final mass. But the envelope of the star continues to grow as infalling material is accreted. After a few million years, thermonuclear fusion begins in its core, then a strong stellar wind is produced which stops the infall of new mass. The protostar is now considered a young star since its mass is fixed, and its future evolution is now set. T Tauri stars. Once a protostar has become a hydrogen-burning star, a strong stellar wind forms, usually along the axis of rotation. Thus, many young stars have a bipolar outflow, a flow of gas out the poles of the star. This is a feature which is easily seen by radio telescopes. This early phase in the life of a star is called the T Tauri phase. One consequence of this collapse is that young T Tauri stars are usually surrounded by massive, opaque, circumstellar disks. These disks gradually accrete onto the stellar surface, and thereby radiate energy both from the disk, infrared wavelengths, and from the position where material falls onto the star at optical and ultraviolet wavelengths. Somehow a fraction of the material accreted onto the star is ejected perpendicular to the disk plane in a highly collimated stellar jet. The circumstellar disk eventually dissipates, probably when planets begin to form. Young stars also have dark spots on their surfaces which are analogous to sunspots but cover a much larger fraction of the surface area of the star. The T Tauri phase is when a star has vigorous surface activity, flares, eruptions, strong stellar winds, variable and irregular light curves. A star in the T Tauri phase can lose up to 50% of its mass before settling down as a main sequence star, thus we call them pre-main sequence stars. T Tauri stars are always found embedded in the clouds of gas from which they were born. One example is the trapezium cluster of stars in the Orion Nebula. The evolution of young stars is from a cluster of protostars deep in a molecular cloud's core, to a cluster of T Tauri stars whose hot surface and stellar winds heat the surrounding gas to form an HII region. HII, pronounced H2, means ionized hydrogen. Later the cluster breaks out, the gas is blown away, and the stars evolve as shown below. Often in galaxies we find clusters of young stars near other young stars. This phenomenon is called supernova-induced star formation. The very massive stars form first and explode into supernova. This makes shock waves into the molecular cloud, causing nearby gas to compress and form more stars. This allows a type of stellar coherence. Young stars are found near other young stars to build up, and is responsible for the pinwheel patterns we see in galaxies. Brown dwarfs. If a protostar forms with a mass less than 0.08 solar masses, its internal temperature never reaches a value high enough for thermonuclear fusion to begin. This failed star is called a brown dwarf, halfway between a planet, like Jupiter, and a star. A star shines because of the thermonuclear reactions in its core, which release enormous amounts of energy by fusing hydrogen into helium. For the fusion reactions to occur, though, the temperature in the star's core must reach at least 3 million kelvins. And because core temperature rises with gravitational pressure, the star must have a minimum mass, about 75 times the mass of the planet Jupiter, or about 8% of the mass of our Sun. A brown dwarf just misses that mark. It is heavier than a gas giant planet but not quite massive enough to be a star. For decades, brown dwarfs were the missing link of celestial bodies, thought to exist but never observed. In 1963, University of Virginia astronomer Shiv Kumar theorized that the same process of gravitational contraction that creates stars from vast clouds of gas and dust would also frequently produce smaller objects. These hypothesized bodies were called black stars or infrared stars before the name brown dwarf was suggested in 1975. The name is a bit misleading. A brown dwarf actually appears red, not brown. In the mid-1980s, astronomers began an intensive search for brown dwarfs, but their early efforts were unsuccessful. It was not until 1995 that they found the first indisputable evidence of their existence. That discovery opened the floodgates. Since then, researchers have detected dozens of the objects. Now observers and theorists are tackling a host of intriguing questions. How many brown dwarfs are there? What is their range of masses? Is there a continuum of objects all the way down to the mass of Jupiter? And did they all originate in the same way? The halt of the collapse of a brown dwarf during its formation occurs because the core becomes degenerate before the start of fusion. With the onset of degeneracy, the pressure cannot increase to the point of ignition of fusion. Brown dwarfs still emit energy, mostly in the IR, due to the potential energy of collapse converted into kinetic energy. There is enough energy from the collapse to cause the brown dwarf to shine for over 15 million years, called the Kelvin-Helmholtz time. Brown dwarfs are important to astronomy since they may be the most common type of star out there and solve the missing mass problem. See cosmology course next term. Brown dwarfs' eventual fate and cool to become black dwarfs. Relative sizes and effective surface temperatures of two recently discovered brown dwarfs, Theta 1 and Gliese 229b, compared to a yellow dwarf star, our Sun, a red dwarf, Gliese 229a, and the planet Jupiter, reveal the transitional qualities of these objects. Brown dwarfs lack sufficient mass, about 80 Jupiters, required to ignite the fusion of hydrogen in their cores, and thus never become true stars. The smallest true stars, red dwarfs, may have cool atmospheric temperatures, less than 4,000 degrees Kelvin, making it difficult for astronomers to distinguish them from brown dwarfs. Giant planets, such as Jupiter, may be much less massive than brown dwarfs, but are about the same diameter, and may contain many of the same molecules in their atmospheres. The challenge for astronomers searching for brown dwarfs is to distinguish between these objects at interstellar distances. Neither planets nor stars, brown dwarfs share properties with both kinds of objects. They are formed in molecular clouds much as stars are, but their atmospheres are reminiscent of the giant gaseous planets. Astronomers are beginning to characterize variations among brown dwarfs with the aim of determining their significance among the galaxy's constituents. In this painting, a young brown dwarf is eclipsed by one of its orbiting planets as seen from the surface of the planet's moon.